Good afternoon again, everybody. Welcome to our next session, and I'm happy to introduce Keith Murray with a very long talk title. You can and should build XKCD's Sky Alarm for cool space things. So, uh, just as an addendum, there may be time for a few questions afterwards, and Keith has said if not, you can catch him out in the hall afterwards. Let's give a hand.
Thank you. Okay. How is audio? That sounds good. Excellent. We are going to be going a little bit quick because we need to. I should actually reset my timer so I'm golden. Now we're going to go a little bit quick. Okay. There we are. Now, you can and should build a sky alarm from the webcomic XKCD. That is what we're going to talk about and the necessary steps to build it. Quick heads up, my name is Keith Murray. My online handle is Keith the EE. The double E stands for electrical engineer, and if you say it really fast, because of the Keith E, it's Keithy. As a quick note, after this talk is done, I'm going to upload the code that is going to be used in these slides and the slides themselves. The URL is going to be broken into github.com, Keith the EE, and then PyCon US 2025. It's also going to sit at the bottom of the slides for the entire presentation. That said, it is hard to see, so hopefully the breakdown of Keith the EE and then PyCon US helps. I'm involved in the Python community in various ways, and one of the common themes in those involvements is outreach and connections, because I like seeing the things people make. Which brings me to the point of the talk. You can and should build a sky alarm from the webcomic XKCD. Now, XKCD is a webcomic of romance, sarcasm, math, and language. It is famously tied to the Python language because of the webcomic import anti-gravity, which is an Easter egg in the Python language where if you import anti-gravity, it will take you to this webcomic where someone is able to fly purely because it is as easy as importing anti-gravity in Python. Now, one of the webcomics that Randall Munroe has is called Sky Alarm. In it, we see a little alarm sitting on a box on a stool, and it's blinking and saying, "Wee wee, something cool is outside. Wee wee, go outside and look up." And the subheader of that is, "I want one." If you mouse over it, it says, "During the day, it also activates for neat clouds and pretty sunsets." You can build it. In this talk, we're going to talk about some of the introductions to the concepts, basic requirements, building a sky alarm, then we'll add some bells and whistles. To build one, we need to break down what is necessary. We have a box with the word sky alarm, we have something to make noise, we have something to blink lights, and we have some way to tell if something cool is happening. Those are our necessary components. This is a great use case for microcontrollers and for sensors, and since this is a Python conference, I'm going to stick with Python courtesy of CircuitPython. Now, it's really easy to build a sky alarm. This is all of the code you need to build a sky alarm. To blink an LED, you're just going to have a LED pixel object, and then you're going to turn it on and turn it off. Quick side note, don't worry about the code in this presentation. It will be available later. The point of the code in this presentation is to show you that when you program on an embedded system, it feels very familiar to the code you're used to in Python. So we've got our blinking lights. Let's make some noise. We're going to use a small electronic called a buzzer, and we are going to make a pin responsible for that buzzer, and when it's time to buzz, it'll turn on, and then it'll turn off. And then we got some imports we need. We have to define the NeoPixel stuff and take care of that, but that's kind of most of it. We have imports setting up pins. We'll put those turning on the light and turning on the buzzer things into a function, and then when a cool space thing is happening, we'll have it go off. That's it. That's most of the talk, actually. Altogether, it looks like this. we've got a little buzzer and a light that's going off whenever a cool space thing is happening, and the buzzer's connected to the pin that we defined as responsible for it, pin A0, and the NeoPixel is the built-in board NeoPixel on there. Okay, I've moved very quickly through a lot of concepts. There's microcontrollers, and then running on them is MicroPython or CircuitPython. Microcontrollers are small embedded circuits that do small tasks. They're usually lower cost, they're lower power, they're lower speed, and they often have lower memory than you would with a full computer. MicroPython is an implementation of a subset of the Python language that is targeted at running on those small microcontrollers. CircuitPython is a fork of MicroPython, and together the two versions of Python work together to build Python that runs better on embedded systems with slightly different priorities. And as one fork gets an advancement, it is usually shared with the other one. Now, not every library will work on CircuitPython and MicroPython because it's not strictly speaking Python. It's a subset of the language standards, and not every microcontroller can run micro or CircuitPython. Additionally, microcontrollers are the small integrated circuits, and the things we were looking at has a microcontroller on it, and it's a full board. It's typically a development board, that way you can get used to using a chip and understanding how to utilize the pins. This gets confusing very quickly, and it's becoming more confusing because chips are becoming much more powerful and are able to do more things, and they're moving closer to a lower power computer in capacity. But that also means that microcontrollers are starting to feel a lot more like the computers you're familiar with, so you can program them relatively easily. To see what kind of development boards you can work with in MicroPython, you can go to micropython.org and go to the downloads page, and it will display the number of boards that MicroPython is built to target. And then that is a version of code that will live on the embedded system and then run MicroPython. Similarly, for circuitpython.org/downloads, you can see the CircuitPython boards that are target. There's a wide variety of types of chips that use this, and so you don't necessarily need to stick with a single brand or architecture, but we're going to kind of sort what we want to focus on to a couple of key features. We're going to be interested in things that have a STEMMA QT port and things that have Wi-Fi because it makes plug and play much easier. Specifically in this talk, we're going to use a Metro ESP32S2 Express. It's a version of a CircuitPython board that has an ESP chip on it. And we're going to use it because I have one and I don't have to solder in order to connect to the pins, and I can pull stuff out of the sockets and I can plug things into the STEMMA QT port. On a CircuitPython drive, you'll end up with a file system. Your main code is going to live in code.py, and then you'll also have a settings.toml file that you can pull your Wi-Fi credentials from, and then wherever you need extra libraries to import, you can use the lib directory. So we have the alarm of the talk, but we don't have the cool space thing of the talk. We're going to take some inspiration from another XKCD webcomic and look at what our problem statement is. We are looking at a problem statement of a cool space thing. Similar, this comic is looking at a problem statement of, I want to take a picture of something and see if it's in a national park, and then see if the photo is of a bird. The first part is relatively easy at this time. You can look up a database. The second part, at the time this comic was written, was a bit harder because identifying whether or not a bird was an image was different prior to the rise of GPTs. We're going to select what part of this problem we're going to talk about. I'm going to say a cool space thing is northern lights. Now, NOAA has a dashboard for forecasting the auroras, and we're going to utilize that. I don't know much about this. NOAA has a ton of information on understanding these, using the dashboards, etc. The neat thing about this to me isn't that I necessarily understand how to use this dashboard, it's that it's really easy to stick a microcontroller into just a corner of my room and then have it query a remote database and then tell me when something cool is happening in that space. So we're going to restrict this to northern lights. The dashboard looks like this. It has a ton of information. It goes through a ton of things, and one of the small things that it's got is a 3-day forecast where it estimates a KP index. KP index is effectively the likelihood that we will see a northern light at a specific region. If you look to where we're at in Pittsburgh, we kind of need about a KP index of 7, but we are going to kind of adjust what we set the alarm to go off to. This is the 3-day forecast. We're going to make the microcontroller grab this, and we're going to look at the recent timestamps in order to identify whether or not we should make our sky alarm go off. Now, there's a lot of information about this on the dashboard, but whether or not we should rush outside to look up also depends on whether or not we have the ability to see northern lights, which in part is something that matters based on light pollution. So we're going to use another website to just kind of get a sense of the light pollution in the region around Pittsburgh. This is an overlay of it. It's really hard to see where the light pollution is and isn't, but the website breaks down Bortle numbers and says that between a green and blue region, you can see a relatively high amount of stars. It's a lower light pollution area. Looking back at the map and upping the contrast, we can see that within a certain region of Pittsburgh, we can get to some low light pollution levels. And that's about an hour's drive from here. So going back to our NOAA database, we're going to set our alarm to go off if the northern lights, or if there is a forecasted KP index of 5 or greater, because that's probably a easy way to determine if the northern lights are happening. There's a lot more we can do. This is not an area I'm an expert in. This is just an area that a microcontroller makes it really easy for me to grab and query some information. So let's grab and query some information. We have to do this on a microcontroller. We'll need to import some libraries. We need to turn on the Wi-Fi radio. That's something that's different than using your laptop to query something. We'll also need to sign on to your network because your laptop normally handles that. But then after that, it feels very familiar. We're going to make a GET request to the server, and then we're just going to parse the data. So our imports look like this. We just have to grab Wi-Fi, connection manager, and requests, and then we initialize the Wi-Fi radio settings on the chip. And then we basically put all of that away into an object called requests, which was designed to feel very similar to the requests library in Python. We also need to sign on to the network. You'll have your SSID and your password stored in that settings.toml file, and then you'll connect to the network using that command. After that, you define that requests object, identify your target URL, and then just make a GET request like you would in most web scraping with Python. Then we have to parse that return text. It's messy, but it's parsing, and you can optimize it as much as you want, but a microcontroller will happily parse this. It's going to just run through there and then look for a specific line that starts off where it has the numbers, offset a specific amount, and then just grab the first day's forecasts of the first 3 KP index values. You can do this for any number of type of interesting things you have on the web. I'm just selecting this for Northern Lights because I want to see a cool space thing. So once we have that aggregated, we're just going to pick the peak KP index, and if that peak KP index is above 5, we have a cool space thing. We can drive an hour from here and then go somewhere. That's the sky alarm. Thank you. That is the talk. Well, okay, we got a little bit of time, so we can do some more stuff. That light was not a fun light. It looked a bit different than the comic. And I used a buzzer, and I hate buzzers, so let's do something with audio, because in CircuitPython, you can do that. So, similar to when we had the single LED on the board, we're going to want an LED strip. The code from just the board was this, and the new code is this. We define which pin we put the LED strip on, and that's going to be the pin that has the data line that says which LEDs should go on. We also have an LED count because we have more than one LEDs. Then we just kind of set the brightness, and then everything else feels familiar to what you've already seen. Doing an animation is added stuff, but it's also kind of familiar to Python. There's a library called Microlab where it implements a subset of NumPy and lets you do some NumPy operations on arrays in Circuit and MicroPython. This way, we not only turn on the lights like we did before, but we have a fading effect, and that fading effect will transition up and down through the LED strip. Then, when we have a reason to call this, we're going to just go through the LEDs and then adjust their fading color and then display them. This is very similar to just set the color for the LED beforehand and then the display. Now, playing sound is similarly kind of familiar. You need to import some libraries, which does a lot of the heavy lifting, but then if you put a WAV file on your microcontroller in that code.py level, settings.toml level, or inside your library level, you can just call it and then open it up and read the WAV file and then point to a specific pin, in this case pin A1, and then put audio there and listen to it. Now, without a quality digital to analog converter, a DAC, it can sound kind of but it's better than a buzzer, and this is all you need to play the audio versus, or when this was how you set up the audio. So altogether, you can plug it in like this without the need to solder. So far, hopefully most of this feels very familiar to the Python you are used to, and being able to just plug more and more things into a microcontroller makes it a lot easier because you don't need to solder things down and commit to something when you're trying to figure something out. So we've got the lights, we've got the sound, and we can stuff it into a little alarm container and make a cool sky alarm. Now, a common theme that you might have noticed throughout this talk is that you can probably do better, which is why I want you to make sky alarms and other cool things to see when other cool things happen, because it is just this easy, and there's lots of opportunities to go further. There's lots of areas where I've made things that will probably break over time, but we have all of the code that we need to set off a sky alarm whenever a cool space thing happens, so long as we define that cool space thing as a specific value of expected EMF radiation from the sun. We can still do more, though. We can give the sky alarm a sense of when. The sky alarm on a microcontroller has no concept of what time it currently is, so we can build a local server and then query that local server and then see when the alarm goes off. That way, if the microcontroller goes out after a period of time, we can look to our server and see when the microcontroller might have gone off. We can also log data using that server. The microcontroller can gather things and put it onto the server and then save it, and then you have a save state, and you have a saved database on a small computer like a Raspberry Pi that can be removed separate from where your sensors are. That way, if your sensors are in an adverse environment, like a high humidity plant garden area, you can still acquire data and do things with CircuitPython without needing to risk the more expensive equipment. We're going to utilize Flask for this task. You can use Fast API, Django, Lightstar, any number of other options, but this is just an option, and it's an easy option. To make a simple Flask server, you just need these imports, then you define the route, and then you return a valid HTML string. To call it, you just use this command. This is a Flask. This is on the intro to Flask page. It's nothing special, so let's start adding some other things. We're going to grab the current time, local, and UTC, and then we're going to package that up into a collection of things called time tuples, because the way the CircuitPython works is it doesn't have 64 bits, so it uses 32 bits, so full timestamps are rather hard. So to pass time between a server and the CircuitPython board, we're going to organize it into a time tuple so that we don't run into overflow errors. Then on the microcontroller, we just need to go and fetch it, similar to the way we went and fetched the information from the NOAA server. So this is our fetch from the NOAA server. Here's our fetch for our current time. Now we're also adding an import for RTC. That is how we're going to do our real-time clock. That takes the struct time and then puts it into a structured packet so that CircuitPython has a similar to datetime package, and you can now figure out what time it is and synchronize that. So if you have an event that the controller triggers, it can go to the server and say, I did this at this time. So our current setup, we have our microcontroller grabbing some information, connecting to a remote server, going to decide if it needs to go off, and then when it does, we have a Flask server to point information at. We also have the sky alarm that goes off. We can take the code we just wrote to connect to the remote server for NOAA, move that to the Flask server, and then sort of optimize what the microcontroller is doing. It should just be able to do the sky alarm information. That way, if you have a reliability issue, your full-fledged Python ecosystem can handle it. The only change, and the reason this code is small, the only change is that wrapper that made CircuitPython seem like requests is now just import requests. The code you wrote in CircuitPython to get data from a server is valid Python code, and all of that fetch code can just live in a .py file on your Python computer. Now, the server has to accept post requests. That way, whatever is running the check remote server to see if a state has occurred can say, oh, hey, a state has occurred. In Flask, that's not a very difficult thing. You can do a bit more protections around it than this, but for a quick demonstration, this is sufficient. Then your server might also want to say, okay, you've posted data to me. If someone wants a GET request, I want to show you the most recent data. So we're going to just load that, and we're going to have the latest thing saved into a specific JSON file, and that's going to be what the web server returns if you query that page. So now we have a microcontroller that has sky alarms and can connect to a local Flask server and can give that local Flask server data if it needs. And the Flask server can also do more. But we can still do more. We can add sensors, because that's the cool part of this. CircuitPython and MicroPython and Adafruit and SparkFun and a few other companies have built an open standard connector called the Stemma Qt or Quick Connector. That way you can plug in I2C sensors into a circuit board and not need to solder, and it works really, really well. In fact, there's a number of I2C enabled sensors that utilize the Quick Connector setup. That way you can go, I would like air quality information, and query the space around you with a sensor while not also having to commit to soldering it in place or having a rat's nest of cables. So SparkFun has options, Adafruit has many options, there's a lot of other vendors, it's an open standard, it's really, really wonderful, and it lets us take sensors that we have and just plug them into our CircuitPython board and utilize that board as a way to grab data. So thinking back to our prior architecture, we can now not only trigger events if a sky alarm event takes place, but we can also gather data and go to a remote server and say, hey, something has happened, let's start doing stuff. To utilize the I2C connector that's built into the board, you're going to have a fairly similar feeling setup to the setting up the speakers, setting up the LEDs. You're going to initialize the I2C, and you're going to tell the controller where the I2C information is going to live. You've got some imports. This is the import for a BME 280, which is just a simple air quality sensor that takes temperature, humidity, and pressure. On the CircuitPython board, your code can just run through and go temperature, humidity, pressure, grab those values, stick it into a packet, and then go to your home server and then send that packet off. The home server can then take it and then decide whether or not different alarms, different microcontrollers in an array that you have for an IoT net should go off. So you really can and should build a sky alarm. It's a fantastic way to explore the space around you and bring Python into your world. Thank you.
So we have time We do have time for a few questions over here.
On one of the previous slides, but wait, we can still do more. You had your board and then you were adding on sensors. What is that? Oh, we just went past it. What is that black lattice-like board that's contained? Could you talk a little bit about that?
Yeah, that is just a piece of machined aluminum, and it's just got some drill holes in it. That way you can take those small sensors and screw them down into place, so you can have a much more rigid way to hold your microcontroller and hold your sensors. You can just use M2 screw and offsets to screw them into place, and it helps you add sensors into a space, have rigidity, and just kind of have it much nicer to stick into a project box than what I had been doing prior to discovering this product, which was finding some really thin plywood and then screwing the sensors down onto it, because I don't like committing to solder, and the ability to pull something apart is really important. So that is just a piece of milled aluminum. Adafruit makes it. I think a few other products make it, or companies make that. It's just nice and convenient. Awesome.
Okay. How about another round of applause, please?
Fantastic.